Welcome to EDU World Space.
So let's take a look at calculating delta H, delta S, and delta G under standard conditions for several chemical reactions. And so if we take a look at the first chemical reaction we're going to do, let's take a look at the reaction between titanium and chlorine. So if we take titanium and chlorine, and we react those together, we're going to wind up with titanium 4 chloride. And we want to calculate delta H, delta S, and delta G. And for each of these, we're going to use a very similar formula. So the delta H of reaction is going to be equal to the sum of the number of moles times the enthalpy of formation of the products minus the sum of the number of moles times the enthalpy of formation of reactants. Same thing applies to the entropy. That should be entropy. So it's going to be the number of moles times the entropy of formation. Of the products minus those of the reactants. And when we go to find the Gibbs free energy, we're going to use that standard equation, delta H naught minus T delta S naught. And since we're doing standard conditions, temperature is going to wind up being 298 Kelvin. Elements in their natural states have enthalpies of formation equal to 0, but their entropies will not be 0. But we can go and look up via table of values each of the entropies of formation for these. So for the titanium chloride, we have 1 mole times our value of negative 763.2 kilojoules per mole, but that's our only product. So we are going to subtract. Now the titanium is in its natural state, so it is 0. And we have also for chloride, it's in its natural state, the chlorine diatomic. So we have 2 moles times 0 as our final amount. So our delta H of this particular reaction is negative 763.2 kilojoules. When we go and do the delta S of reaction, we're going to go do the same thing, but the values will not be 0 for the enthalpies of formation for the elements in their natural state. So the enthalpy for the titanium tetrachloride is 354.9, 1 mole of that. And now when we do our reactants, we have 1 mole of titanium at 30.76. And then the sigma means sum of, so we're going to add the 2 moles of chlorine, which is 222.96. And we're going to get that value as negative 121.8 joules per Kelvin. But to convert that into and use it for delta G, we're going to wind up taking a look at negative 0.1218 kilojoules per Kelvin. Now at 298, we can use delta H minus T delta S. So we have our negative 763.2 minus 298 times our negative 0.1218. And when we put that into the calculator, we get negative 726.9 kilojoules. For our delta G. And we can do this same thing for two other chemical reactions. Process will be exactly the same. So if we take a look at C2H6 gas plus 7 chlorines forms 2 CCl4s and 6 hydrogen chlorides. We can follow that same process for all of these. Products minus reactants. So we have 2 CCl4s, and that delta H is negative 106.7 kilojoules. We sum it up, so we add our 6 HCl's, and the delta H for those is negative 92.3 kilojoules. Those are our products. So now we're going to subtract the sum of our reactants. So we have 1 mole of C2H6 with its H of formation of negative 84.68. And we're going to add the 7 of chlorine. But chlorine in its natural state has a value of 0. And when we do that math, we're going to get negative 682.5 kilojoules. And we go find the delta S. We're going to wind up doing the same thing. So you can see how it's going to look very similar, although the values for the entropy will change. So we've got 309.4 joules per Kelvin. We have 6 moles of HCl, and its value is 186.69. We're going to subtract the reactants. And so the C2H6 is 229.5. And our chlorine is going to be 222.96. Remember, the answer here is going to be in joules per Kelvin. We want it in kilojoules, so we're going to divide by 1,000. And so we're going to get our answer as negative 51. I'm sorry, it's going to wind up being divided by 1,000. Negative 0.0514 kilojoules. And if we want to go do our delta G, I should say, we're going to do delta H minus T delta S. So we're going to have our negative 682.5 minus 298 Kelvin, because this is under standard conditions, times delta S, which is negative 0.0514. And if we go do the math, we will get negative 667.2 kilojoules. Now, as an alternative, if you wanted in both of these cases and in the third case that we do, you could go look up the delta G values. And if you use the delta G values in a table of values that you find, you might find that the answer for delta G is slightly different than the answer you see here. It just depends on which form of the equation you use. Let's do one more example. Let's go ahead and take a look at barium oxide and carbon dioxide and form barium carbonate. So the process here again will be the same. Products minus reactants, and in this case we have 1 mole of each of our substances. So we're going to have 1 mole of barium carbonate with its enthalpy of formation as negative 1216.3 kilojoules. We're going to subtract the sum of the 2 reactants. Each is 1 mole. And for the barium oxide, our enthalpy value is negative 553.5. We're going to add that to our 1 mole of CO2 with its value of negative 393.5 to get the delta H of reaction to be negative 269.3 kilojoules. We'll do the same thing for our entropy. Again, 1 mole of barium carbonate. It has an entropy of formation of 112.1 joules per mole Kelvin. On the reactant side, 1 mole of barium oxide with an entropy of 70.42 joules per Kelvin. And our carbon dioxide with a value of 213.6 joules per Kelvin. We're going to wind up with a delta S of negative 171.9 joules per Kelvin. But again, we're going to want that in kilojoules. So that's going to be negative 0.1719 kilojoules per Kelvin. And we'll go ahead and we'll use delta H minus T delta S again to find the Gibbs free energy because we just calculated those 2 values. And if we plug those numbers in, the delta G of reaction is negative 218.1 kilojoules. So again, you could have used the delta G thermodynamic data of those formations to come up with a value for the Gibbs free energy of reaction, and the answer might be slightly different than what we get using delta H minus T delta S. So which one of these 3 reactions are spontaneous? Well, if we go back to number 1, it has a negative delta G. So the first one is spontaneous. The second one has a negative delta G. It is spontaneous. And the third one has a negative delta G. It is spontaneous. So all of the reactions are spontaneous. All with our negative delta G values. And what would happen to the delta G if we wound up increasing the temperature of our system? What would happen to its value? And so if you take a look at any one of the 3 equations, what we can see is that in each case we have a negative delta H and a negative delta S. If we take a look at another reaction, negative delta H, negative delta S, we take a look at the third one. We have a negative delta H, negative delta S. So in all cases, if we have a negative delta H and a negative delta S, what that means is that if we increase T, we're going to wind up having a value of this negative T delta S that is going to wind up making the system overall become more positive, right? Because this negative times a negative is going to altogether wind up being positive. So the higher this T value is, the more positive the entire term becomes, and the more positive the delta G will be.